very important session, data, data, data. I love that title, by the way, whoever named that. Before I hand it over to our first speaker, I just wanted to reiterate some comments from past speakers, namely Adrian Ansare and Kumboso and Naomi. I apologize if I mispronounce your names, but you were both presenting your onset and osmosis models for your countries, Kenya and Zambia, and very explicitly highlighted the need for better access to quality data, improved data collection methods and management, as well as improved collaboration between different stakeholders. And I thought that that was very timely, based that we have a lot of different stakeholders in this panelist. So in light of this, I just wanted to invite others in the audience to post their questions in the Slido to the panelists on this very important topic. So without any further ado, I will hand it over to our first speaker, who is Benjamin Stewart, who leads the Global Operations Support Team, GHOST, at the World Bank. His work is focused on introducing novel geospatial analytics to World Bank operations, with special focus on energy planning, satellite remote sensing, and open data and tool development. So over to you, Ben.
There you go. Thanks. Thanks, Nicolina. Thanks for the introduction. Let me just share my screen. I hope everyone can see me. See what I got here?
Yes.
Okay, great. So yeah, good morning, afternoon, evening, wherever you're dialing in from. Thanks. My name is Ben Stewart, Senior Geographer leading our Global Operations Support Team, the World Bank's data group. I've been supporting the energy unit at the Bank for a number of years, most notably through the development of the Global Electrification Platform, and through which we have supported this Chester Summer School a number of times. I think this is probably the third or fourth iteration which was supported. I'm really quite sorry to have missed the in-person training this year, but I'm happy today to be able to talk to you about data, which is really a part of what it is I do on a regular basis. So I think a lot of this presentation people have seen before, so I will go through it fairly quickly, leaving plenty of time for discussions and the presenters. So I'm going to sort of pose 3 questions that the Global Electrification Platform aims to answer. The first being, how much will it cost to reach universal electrification? How many people will be affected? And what solutions will be used? So those questions we attempt to answer through the Global Electrification Platform. It is an implementation of the onset algorithm developed by KTH, where for each country with less than 80% electrification, we develop approximately 100 least cost electrification solutions. The platform allows you to explore the results of those scenarios, but it includes links to all of our other open innovations, our GitHub repository, our online documentation, the data that's stored in energydata.info. There's lots of sort of secondary and tertiary data sets. And I would encourage, if you haven't been here before, I would encourage you to visit electrifynow.energydata.info, and you can start exploring sort of at your leisure. Quickly looking at the landing page for a specific country, I chose Ghana. It's a country I've been to Accra, and it's also a nice rectangular country, fits nicely in maps. So here's the landing page. On the left side, we can see a series of radio buttons that allows us to explore the scenarios, right? So as I mentioned, we have approximately 100 scenarios, but for those of you who have been in the onset course, you're aware that there are many more parameters than the 7 that we expose here. So yeah, combining these various what we call levers, by the scenario levers, by the combination of these 7 gets you to the 100 scenarios we're looking at, and allows you to change things like the demand targets, the inclusion of non-residential demand, PV and grid cost, and then the final 2 options are about specific rollout, whether there's a cap on intermediate investments or whether we force grid connection within a certain distance of the grid. That's an important policy determination for a lot of World Bank work. So yeah, there are 7 variables exposed here, and for each of those variables, we have 2 or 3 options. In the onset model, we have hundreds of options, parameters that can be configured. So just to say, like, while there are lots of scenarios here, that's why we are so focused on open innovation and open tool development, because there's so much more that could be done if you're willing to sort of go deep and learn about the details of the tools and the platforms. So below the scenario, we also on the right side have sort of overall summaries of what the different scenarios entail. But we also have the ability, you can see down here, down here in the bottom, we have the ability to look at intermediate time steps, right? Right now we're looking at what is the results of universal electrification by 2030. But in doing so, we also have an intermediate time step as in what does it look like in 2025. We also have the ability to, on the right-hand side at the bottom, you can see the download button. This allows you to download the results, either PDF maps, or you can go directly to the energydata.info page and download all the specific data, right, from the settlement shapefiles to the CSV scenario results. Like out here, you can see it says 95 results of this particular iteration, as well as understand more about the modeling parameters. You can really dive deep on what these data sets really look like. I wanted to share sort of a combined map of Africa. This is the default scenario, sort of all blended together. I think I quite like this map. It can teach us a lot about the breakdown of technologies, and really also the breakdown of population across the continent. There's obviously areas of denser population and less population, and that drives a lot of the solutions that would be required, that would be available for this. So as mentioned, right, the idea is that like this is the results of these default scenarios, but there's lots of other additional aspects that we've developed, right? This is the Explorer, but we also have the toolbox and the generator, which allow you to sort of generate your own model runs. We've also done a lot of capacity building, right, through things such as the summer school. Okay, so required investment. We expect it to cost $191 billion US. 71% of that will be invested in the grid, 20% in standalone photovoltaic, and the 8 to 10% in mini grids. But I think what's most important with these discussions of data, and I think Adrian mentioned it in his onset examples for Kenya, is that data drives a lot of these decisions, right? So if we look at the default scenario, and this is the number that I quote most often from the GEP, is this idea of $190 billion US to reach universal electrification in sub-Saharan Africa. However, if we just go for the cheapest solution, it's about 68 billion. And if we go to the most expensive solution, it's about a $420 billion investment. That's a $350 billion decision. This is going to be based on the quality of the data and the assumptions that we base underneath. This isn't published anywhere yet. I've been trying to think of how to do it, but looking at the data, the two most important determining factors I find in comparing these onset solutions are quality input data, right? So data on the transmission networks and on the distribution of energy. And that's a question of quality data, right? That's come up from a bunch of our presentations earlier. The idea that, well, I'm working with data, but it's out of date, or I'm working with data, but it's incomplete. So quality geospatial input data is one of the primary factors. The second most important factor that I see based on the model parameters is the question of demand. Right, and demand is based on the assumptions we make, and I think that sort of questions of demand are one of the reasons why we want to get these tools in the hands of country experts and country practitioners, because demand is going to change substantially through time. So we need these models to sort of iterate and live and be live documents. So what can be done to improve data? I've got sort of three things that I think that we're pushing at in the data group at the World Bank. One is to encourage and enable countries to be open with their data. We talk a lot about open data, and the World Bank's made great strides in the past decade, but it's one thing to say it, it's another thing to do it. The next is to sort of train public policy experts and country partners on the value of open data, right? So there is a return on investment for making data open. And finally, to continue to support open data solutions. I guess I can go to the energydata.info portal, because oftentimes, like I say, we say that data should be made open, but if there are no tools or platforms through which, if every country has to sort of host their own open data solutions, then that many times becomes quite onerous. And there's also a lack of compatibility. So energydata.info is a good example of a World Bank-led initiative to make energy data of all types available to the public. Now, I could talk for a long time on the nature of open data portals, but this is a great example of what I would describe as similar to like HDX or the World Bank's Development Data Hub. It's a large, flexible data depository. It's low on technical requirements or schemas, but it's also low on functionality. But what it has is volume. It's just a place to sort of dump a lot of data. So if you finish a project and you want to be able to say, well, I made the data public, you can go to energydata.info, register, and put it there. and then someone else can get access to it. This is a great starting point for being open. Another example that we've been working on a lot recently is the Lights Every Night repository. This is sort of every night of nighttime lights imagery is available to the public. I actually checked this morning, we have 460,000 individual images measuring approximately 70 terabytes of data. And this is all hosted for free by AWS. Our colleagues at NOAA do the processing, and then AWS hosts it for free through their AWS for Good program. And that enables us to look at something that open data allows us to do analysis like the high resolution access indicator. Somebody had mentioned this in another, it was a question in another presentation. I wrote it down, but didn't write down the name. The idea that electrification is not binary yes and no. We often think about that in our modeling, but really energy access is a quality metric. Like I think it was the idea that if you're electrified but only get electricity 2 hours a day, should you be considered electrified for universal electrification? And the HREA takes the history of the nighttime lights imagery, and it sort of looks at, well, if this place is electrified, how consistently is it electrified, and what does that mean? So I'd like to actually sort of encourage the people who have done specifically some of the onset training to think, how could a non-binary method of electrification be incorporated into those models? So I'm already 40 seconds over time, so I'll say thanks and hand it over back to Nicolina.
Thank you very much, Ben. So next up, we have Roberta Quadrelli. She is the head of the section in the Energy Data Center of IEA, overseeing data and indicators for energy transitions, SDGs, and national energy data capacities. Roberta previously headed this section working on non-member countries' data, and her background is in climate research and research management. At IEA, Roberta's experience has been on data for energy balances, emissions, efficiency, innovation, and includes contributions to IPCC assessments and guidelines, and to methodologies on energy statistics, SDGs, and efficiency indicators. So I hand over the mic to Roberta. Thank you. I think you're still muted, Roberta. I don't know if you can hear us. I can see you. Are you able to hear us? You seem frozen, so I hope it's not on my end.
It's frozen for us as well on our end.
Okay, in the interest of time, maybe we should jump to Sebastian. Sebastian, are you ready to jump in now, if that's possible?
Yes, I am. I'm here.
Okay, then let's run to you. I'll just give a quick intro, and then we can start with Sebastian and then jump back to Roberta. So Sebastian Sterl, he works as an Associate Program Officer for Energy Planning and Modeling in Africa at the International Renewable Energy Agency, IRENA, an applied physicist, sorry, that's a really tricky word, an engineer by training. He specialized in the technical and policy-related aspects of renewable electricity generation and of climate change mitigation, with a focus on sub-Saharan Africa. So, Sebastian, please take it away.
Thank you very much, Nicolina, for giving me the floor. So I'd like to talk today about a new concept that has been developed by the International Renewable Energy Agency, IRENA, called Model Supply Regions, which is a way of providing model-ready databases on variable renewable electricity resources tailored to the African continent and energy models for Africa. But let me start with giving you the background of why we think this is necessary. So whenever we do exercises using capacity expansion models for African countries, we typically find pictures such as this one. What do we see here? This is from an IRENA report on Eastern and Southern Africa from a couple of months ago. The horizontal axis shows time until 2040, and the vertical axis shows total installed capacity. And what the graph shows, the stacked colors show, is the total existing and committed capacity of power plants in that region. And the red line, the rising red line, is peak demand. So we can already conclude that existing and committed capacity generally will not be enough to meet future demand. And this is a picture that will emerge for almost every African country that we investigate, because demand is simply rising so fast. So there's a gap and we're going to need new technologies to close the gap. That is why we use models based on cost optimization to try to pick the best technologies from a range of solutions for closing that gap. Now, variable renewables such as solar and wind power can obviously be a part of that solution, but they need to be well represented in the models because they have specific characteristics that must be taken into account. So how do we do that? It's not such an easy question. If you'd look at, for example, hydropower projects, it's quite simple. You would simply take the specific projects that are candidates for being built and input them in the model with specific technical characteristics and cost data. But you can build solar plants pretty much anywhere on the African continent. And there's a great range of regions where wind power is viable too. But we cannot simply put every single pixel of the African continent into an energy model. It will be way too heavy. It's impractical. At the same time, we still do want to represent the diversity of resources because different regions have different seasonal cycles, and for wind power also different daily cycles typically. So where do we strike the balance? So the problem is that existing databases such as the Global Solar or Global Wind Atlas are good for giving the overall picture, but the data is not model ready. So we want to have a representative sample of each country's overall potential in the model, so the model can investigate how well this would perform, these potential projects would perform as compared to other options. So we set out with the idea of finding a subset of what we could deem the most attractive locations for solar and wind park deployment in each country to be included as option in capacity expansion models. What does that mean? Most attractive locations. As criterion for attractive, we use the expected levelized cost of electricity of a project, including the costs of grid expansion. So if you have a resource that's far away from existing grids, we take into account the extra costs for developing additional transmission lines, building additional substations, and so on in this LCOE. So that means we take into account simultaneously the resource quality. The better the resource, the lower the LCOE, as well as the distance from grid. The further away, the higher the additional costs for lines and roads. We obviously exclude unsuitable and protected areas, and then we can do a screening by LCOE and take a subset to get an all-Africa dataset. So graphically, how does it work? We start here on the left-hand side with the country's overall resource potential, for example, based on irradiation and temperature for solar PV, or based on wind speeds for wind power. Then in step 2, we exclude the unsuitable areas. In step 3, we extract the overall potential. In step 4, we cut that potential up into smaller regions that each represent the typical size of a utility scale project. We calculate for each of those regions the attributes such as total potential, average capacity factor, hourly profiles, total costs for grid expansion, and so on. And then in step 5, we screen all these sites from lowest to highest LCOE and take a certain subset. What we typically work with is screening up to 5% of a country's surface area. So this is the same example, but for wind power. This is the map for all Africa. So we do this process separately for each single country on the African continent. In yellow, solar PV, and in wind, in the green, onshore wind. Now this data set has several characteristics. Good to remember, it represents the cheapest locations within each country. We achieve a very high spatial and temporal resolution, kilometer scale, hourly, thanks to the openly available data sources that this work is based on. And these all represent possible individual projects with at gigawatt scale. Since we are looking at not only the geographic distribution, but also the attributes in terms of cost and performance of all these locations, we are easily able to extract diurnal and seasonal profiles and include that information in capacity expansion models. And it also allows us to sort of investigate this balance to be struck between exploiting excellent resource quality, but also limiting the additional costs for grid expansion. One interesting finding here that I'd like to share is that we obviously know that solar resources generally are spatially a lot less divergent than wind resources. So therefore, we find the solar model supply regions, again, the cheapest ones in each country, to be typically 5 to 6 times closer to existing grid infrastructure than the cheapest wind model supply regions. This is an example for Madagascar on the right-hand side. Again, yellow for solar, green for wind. These already represent the 5% cheapest locations. Those for solar PV cluster around the existing grid infrastructure because resources are spatially not so divergent. It's cheapest to stay close to grid. For wind power, it makes sense to expand the grid to exploit excellent far from grid resources. We can also compare these model supply regions across the entire continent, for example, by quantifying the LCOE. You see it here on the map for solar PV and wind. The darker the color, the lower the LCOE, and therefore the more attractive the resource. Where do we find the most attractive resources? We find them in a shape that stretches from northwest to northeast and back to southwest Africa, for which I would like to coin the term African resource boomerang. We are also able then to see for each country what is the effect of existing or non-existing grid infrastructure on the expected LCOE. So each dot in this graph represents a country. X-axis is average solar PV capacity factor. Y-axis is expected levelized cost of electricity based on 2020 CapEx and OpEx values from IRENA. And we do see there is some spread in this point cloud. That means that, for example, SO, Somalia, would require higher LCOEs than Namibia, even though resource quality is roughly the same because the grid is better developed in Namibia. Of course, this will shift in the future. The cheaper these resources get, the lower the CapEx and OpEx, the more the balance will shift in favor of exploiting near grid resources. How do we enter this data in energy models? We have a mathematical method to cluster these model supply regions spatially, so regions that have similar let's say temporal profiles, similar performance and availabilities, and we can include each cluster as a separate technology in our capacity expansion models. Here you see an example for solar PV clusters in Ethiopia. So we've got 10 clusters, 10 separate technologies with separate costs and performance characteristics included in the model, and the same here for Niger. So we can see that this method nicely spatially clusters very similar regions with similar resources. So to close off the presentation, a few final remarks. This methodology, these data sets provide model-ready zones for solar PV and wind deployment to be included in energy models to bridge the gap between highly detailed resource data sets on one hand and what is practical for energy models on the other. The selection in the end of which MSRs will be part of the final solution of these energy models, of course, happens based on the cost optimization of the entire system. So the hourly shapes will play a role. We've developed an additional clustering method, as I said, to help reduce runtimes of models. And we need to remember here, the strongest resources are not necessarily the cheapest. That's what this analysis shows, because you have the grid expansion component, but the cheapest resources are also not necessarily the most optimal, because from a system point of view, the temporal profiles also matter. These data are available. They are already open sourced on the internet. You can find the link on this previous slide. So there is a Zenodo repository where we host these maps, Excel files, and shapefiles. The code is available on GitHub, and we are available for answering any questions. I hope this has been very interesting, and back to you, Nicolina. Thank you.
There we go. Thank you very much, Sebastian. Indeed, very interesting. And I believe we have now Roberta ready to do her remarks as well. So thank you. Over to you.
Thank you very much. Sorry about this. I think this was my best entrance ever, crashing everything. So remember. So thank you very much, Nicolina, and thanks to organizers for inviting the IEA to this panel on data, which is very important today. Just taking a step backward compared to the previous speakers, within the policy advisory role, the IEA is really a great data integrator for energy information at global scale. We are in constant dialogue with governments primarily to collect data that then we recompile into these comparable international databases. But also we work with governments also to recommend how to improve data work, resources, strategies on statistics at national level, which is very important because we rely a lot on the national efforts. This is a point I wanted to make, first of all. This was my first message. I just like to stress once again that data should be considered an integral part of any policy work in terms of all the stages of the policy work before to inform the policy at the time of planning, and then during policy implementation to monitor what happens, and after the policy to evaluate the impacts and to inform successive efforts on the improvement of that policy. So it's very important to convince our counterparts, stakeholders at the government level in every country to invest in high quality data that are relevant to each level of policy. So this can be very high level macroeconomic, like SDGs, Sustainable Development Goal 7, IEA strongly engaged with a lot of governments and the UN on this process as we are custodians, but also down to the level of granular individual measures. This is important. So we need to have relevant data also, not any data. And instead of explaining once again why it's important to have good data, this is an example of a situation where there were no good data. So maybe it's more impactful, in fact. This is a real example taken from a partner country of the IEA, and the country with a nice ambition wanted to integrate in their policies some minimum energy performance standards for, in this case, it's cooling equipment, but it doesn't really matter. So they were saying, we don't want anything anymore that is lower than a certain efficiency level. So on the y-axis, you see this energy efficiency ratings. In fact, what they did is to set a level without having any information on the market situation. They set it at this level that is around 8 here, you can see. So it's a good initiative to have a good policy to improve the market efficiency, but there was no information. And in fact, later on, this is the situation after collecting data from the market, national and regional. All the scattered points are the efficiency ratings of the various equipment models in the market. You see that they were already above the threshold, so they were already more efficient. This is a very striking example of a policy that was completely useless. There was no effect at all on the market. In fact, they didn't feel it because they were above this minimum level. So it's a policy failure. It's not really great to see. For information, this country improved their policy in later years. But also policymakers are sensitive to money discussions. So this is another example I took from one of our members. So it's very relevant. It's an important country. They were projecting, because clearly we are talking about the modeling planning here as well, so equally for policy and for modeling, the data are important. They were projecting electricity demand based on GDP. In previous years, this had worked, so they said, okay, electricity demand will always increase like with GDP, and that was the dashed lines are projections at any point in time, so they were continuing with this linear sort of extrapolation. And at a point, the demand was not anymore following the GDP growth. And in fact, you see the evolution is quite different. And only after integration of the demand side for electricity, the evolution in projections as well changed quite significantly. I was very happy the previous speaker mentioned demand. So here we are talking about billions of overinvestment, so a lot of money wasted in infrastructure and increased prices for electricity. So this has a strong impact compared to the cost of data. The second message I wanted to give is also to think of the energy system as a whole and not only the supply part. Sometimes we are really happy. We think we are happy when we know, okay, gas, oil, renewable, etc. This is I'm showing through an example of a very hot question, like now everybody wants to know how much we rely on imports from Russia. This is an example from Italy, so you see a lot of gas, some oil, some coal. And we think we understand, but in fact, if we want to understand very well how to plan our secure energy future, then we need to understand what are the drivers of that use of energy. So where do we really use gas, coal, and oil? And this requires that we really understand what happens at the sectoral level. This is manufacturing, services, residential, transport. So we have a variety of users in the demand. And if we don't think of the energy system as a whole, it's really very difficult to make good projections and modeling for our energy transition, so for our long term. And that's why at the IEA we also strongly push the sort of development of more granular data This is an example. So across each sector, you can have subsectors or end uses, like in transport. Is it freight? Is it passenger? Is it rail? Is it maybe in passenger cars or buses, etc.? So we need to understand, because each end use has different evolution. And for our planning and modeling, this will be driven by different dynamics in the future. So our little promotion, because also tomorrow we release a new database on energy efficiency indicators, so data at this level of granularity that we are trying to promote more globally, because unfortunately this is more complex to collect in terms of information. You have a larger number of players compared to few suppliers of energy. So here we enter a bit of complexity also for countries to track what happens within their territories. This is a little quiz for our listeners. Two countries I took it from our data, just to show that the disaggregation, once we look at energy use in households, in residential, but in fact the drivers can be very, very different. So in one case you have a huge predominance of space heating, in the other case you have a large cooking and appliances shares. So if people want to guess what these countries are, there'll be important prizes later on. I'm joking. If anybody has ideas why this could be so different, or at least how to characterize these economies, I will provide the answer soon if there is no, because we don't have a lot of time. But it's really important to think in terms of what drivers our energy consumption has. Okay, so I give the answer now. So one was Italy. No preference from me, of course. One is Brazil, so completely different. So each country has a very different picture. And if you look globally, the IEA, in our experience, what we see is that, in fact, for most countries, we don't have this understanding, in fact. And this is where we need to put more effort to understand the granularity of energy demand, I would say. IEA has a lot of activity in the training and capacity building areas. So this is an example of manual, but we have a training activity, etc. So this was just my conclusion. Importance of data, thinking of the energy system, in particular looking at energy demand, and really supporting better quality data at the national level before we extract it as international compilations. So IEA happy to work with partners in these areas, and thank you very much for this opportunity. Sorry about the problem before.
Thank you very much, Roberta. And now, last but not least, we have Naomi Tan, who is a PhD student at Laguerre University and research assistant at the Imperial College in London, working for the Climate Compatible Growth Programme. Her research focuses on the process from raw data to policymaking and investment, and where energy modeling is used to accelerate low carbon transition. So the floor is yours, Naomi.
Thank you. Thanks, Nicolina. I'm very happy to be contributing to the data session. So I guess the first question is, why is data so important? What can it contribute to? Well, data can be used for policymaking, and evidence-based policymaking has two goals. To use what we already know from program evaluation to make policy decisions, and to build more knowledge to better inform future decisions. So this approach prioritizes rigorous research findings, data, analytics, and evaluation of new innovations from anecdotes, ideology, marketing, and inertia around the status quo. But how do we do this? How do we start? Developing a national decarbonization strategy requires significant investment, often from donors paying consultants. So the first investment is to develop a set of data and initial investment models. After this, analysis can be quickly updated, adapted, adopted, and applied. And that analysis can be used to set clear, quantified policy targets and underpin loan applications. It can also be incorporated into fast policy analysis and slower burn academic processes. And this is where the CCG starter data kits come in. So CCG, with partners, are co-creating and providing free starter data kits for most developing countries to help kickstart this process. So currently we have 69 free starter data kits for countries in Africa, Asia, Oceania, and South America, which can be seen in this map. We're also currently developing an additional 11 starter data kits to include countries such as Japan, China, Mexico, and Bangladesh, so pushing about 69 to 80. The explanatory preprint articles are on Research Square, and data sets are on Zenodo, and they're all freely accessible online. And the data has been calibrated to develop net zero emission scenarios for each country. The output and process employed are documented as is a summary of process, and they are very useful for development partners, consultancies, national investment analysts, and academics. And they can also be used to facilitate a number of engagements between countries and support organizations. So on the right over here, you will see an example poster from one of our participants in the summer school. So they have been using our starter kits to create investment models for their country. And here's another one on the decarbonization of Kenya's power system, done by Imperial College London. And also, the starter data kits have been used by CCG for country engagement. So we have done this with Vietnam in the last few months. And lastly, the starter data kits help to overcome barriers of data inaccessibility, which is a current problem around the world. So the plan for this year's starter data investment kits is to build on the successful launch of last year's starter data kits. And I put on the screen here our website to the starter data kits. If you type in climatecompatible.com/starter kits, you will find all the starter kits for our 69 countries on the webpage. So I said we're building on from the 2021 starter data kits, and the kits are being developed to support capacity building, national growth and decarbonization analysis, support IFI processes, including the Paris Alignment, World Bank Group's country climate and development reports, and the Green Climate Fund country programs. And the effort for this should be good enough to screen for readiness or pre-feasibility funding. And lastly, they will provide a faster start for analysis with core tools used in CCG and beyond. So the aim of the data kits is to produce outputs that are good enough for general finance pre-screening for a set of, say, general NDCs. Their outputs are to be set up so that scripting to develop inputs, a broad range of models and analysis is possible. And the prototypes of the 2021 certificates demonstrated that this was possible for most. And I should add that a country that is being used as an inspiration for this effort is Costa Rica, who have co-created a similar process to develop policy and successfully apply for funding from the ICTP, World Bank Group, and Green Climate Fund. So currently, a little bit more about the 2022 starter investment data kits. Along with the SLOCAT organization, CCG has gathered transport data for 25 countries, and this includes passenger per km, ton per km, and number of fleet by mode. And all of these, all this data can be used on MAED, M-A-E-D, which is a tool developed by the IAEA to predict energy demand. So our plan is to gather free open source transport data for our 69 countries that we have starter data kits for, and then expand that to 80 when we have the additional 11 starter data kits, to create simple investment models for them. And to summarize this whole process, I put here a diagram from raw data to policy and investment. So our first stage here is raw data, so this will involve satellite maps and databases. Our second bit is data pipelines, so this involves the methodology paper, scripts, coding. Our third point is the starter data kits, which I mentioned before. We have 69 of them, and they're all freely accessible on our website, on Zenodo and Research Square. The fourth bit, application and analysis, involves our tools, the tools associated with CCG. So the tools have been used for this summer school, and that includes Clues, EBS, FinPlan, Flex Tool, Onset, May, Muse. And there are also a few additional ones here that were not part of the summer school, for example, Matt, BP, and Team. We also have a set of open learn online courses, so they can be accessed online. You'll get a certificate from this. Basically, this is self-learning for you to learn how to use these tools. We also have a YouTube collection So these are videos to help you understand the tools, and it should be alongside the Open Learn collection. We also have an online troubleshooting support group, so this is on Google, and we also have capacity building events throughout the year. So for example, this ICTP summer school, and also the energy modeling platform, which we are currently organizing and should happen at around the end of November or December. And there is also the energy modeling platform Latin America, which being organized by a high-risk team at the University of Costa Rica, which will happen at around September. And after this, there is policy process. So the analysis to support policy making, and concessionary finance screening. So analysis to support developer funding. So I hope this is a good diagram to simplify what I've been talking about in the past few slides. And that is it from me today. A very short presentation as I'm worried about time. But if you'd like to know more, feel free to ask a question or contact me on LinkedIn. Or if you would like to know more about climate compatible growth, please follow them on LinkedIn as well. Thank you.
Thank you very much, Naomi, and a special thank you for rushing up there so that we could finish on time for the discussion, which hopefully will be a very fruitful part of this intervention. So I will start by actually turning to the questions that have come in online. So please feel free to add further questions in the Slido. That the link is in the chat. But I will start with two questions that are actually linked. And they are related to energy demand. So I will direct this question to Roberta. And the first one is, how can we communicate to stakeholders this uncertainty in demand estimates and ensure that our models outputs are robust? And paired with that would be, what are the main factors to take into account for energy demand growth? So over to you, Roberta.
Thank you for the difficult questions, Nicolina. I start with the second because we have some methodological framework that shows the various disaggregation of end uses across all the sectors, so how demand really is driven. I showed some examples in the slide, but the book there, this manual, shows really systematically each sector what driving uses. Some were also in the previous presentation, so I'm happy to see that there is picking up this sort of granular information, the intensity like passenger kilometer, etc. My assessment is that these data are scarce globally, so that's where we try to promote also more work in this area from government. So the uncertainty, maybe the messages of the type I shared, like the huge mistakes that some governments make in the absence of this demand assessments, may be more convincing than maybe an uncertainty number, you know, because you can show very different evolution. If you have, for example, space cooling, and you know that with climate change, you'll have much more needs in space cooling, you need to know that there is that sort of what we call activity, like service, that will take more room in the future. So I'm also welcoming tips to convince stakeholders about the importance of such data, because we want to promote this data. Maybe together we can have a better message, because IEA is also trying to expand the coverage, but we are not yet global as we would wish to be. Thank you.
Thank you very much, Roberta. And I think that sort of provides a good segue over to Sebastian as well, if you would also want to touch upon this question, or else address the question on how the international community plays a critical role in enabling both access to and increasing the quality of data in general, if you wouldn't mind addressing either of those two, and please try to keep it as a few lines. Thank you.
Yeah, no, I absolutely agree. There are still big gaps in terms of data that is needed to really critically assess different elements of the of clean energy transitions. I showed one example of a data set that, in our opinion, closes some gaps that exist, but there are many more. that we need to look at. On the demand side, as has been said, there's a lot of uncertainty around future trajectories. How is electrification and demand growth going to impact all that? How are load curves going to look like? What is the impact of sectoral coupling going to be? So there's, I mean, scientists won't be bored in the coming years.
Thank you very much. And then turning to you, Ben, I will first reuse a term that you actually dropped the other day in a side conversation on how we need to zoom out from the primary reuse of data and actually focus a bit more on the reuse of data that we are collecting or producing. So if you wouldn't mind expanding on that, and also how the World Bank can enable the reuse of data. And then also, I just saw a comment coming in from the chat regarding standards for specifying the level of uncertainty in data. So I'm throwing that to the mix, and you can please.
Yeah. There's a lot to touch there. I think the specific, we talked about the idea of reusability being more important than usability is a term I've been talking to people about it internally, because more and more as we enter an open data world, data will be used more sort of in secondary and tertiary projects than it will in the primary project, right? If you collect data and store it somewhere, you can use it for your project, fine. It'll be used more times later. So if we think about that as a primary driving factor in our data collection, we start thinking about, well, we need to document it better. We need to maybe collect other information when that might not necessarily be important to the original purpose, but might be useful later. I'm thinking of something like you're walking around collecting information on telephone poles or local distribution networks. That's great, but maybe some of the attributes that you're collecting are useful for your project, but you might want to collect secondary attributes as well while you're moving around. Or you might want to collect secondary data completely independent of those poles. I'm thinking of GPS tracks to be included in an OpenStreetMap in order to do better georeferencing of roads and buildings. That came up in a project just this morning. So yeah, I think that's really interesting, is to start thinking of your data as a public good every time it's collected. The question of uncertainty is a great question. It's one that we struggle with regularly, whether it's for, I think actually a lot of energy data, especially in the renewable energy space, uncertainty is actually fairly well documented. I think that something like, the certainty and uncertainty in the global solar and wind potential maps is available. Like there are measures of uncertainty. I've become very interested recently in some of the more commonly used vector data sets, things like building footprints and roads. There's uncertainty in those, right? These are model derived products, and we take them as verbatim that this data set I have on the vector representation of building footprints is correct, but each of those footprints has a confidence associated with it. And if we, the data producer chose a confidence that they are going to do that they thought was appropriate, but we don't know if that's appropriate everywhere, right? And one of the things, again, very preliminary, we found is that the quality of the data is worse in poor places, right? So if these places are already sort of low income, low poverty, now they have low confidence in their data. This is only going to exacerbate a lot of our analytics. So I think that's something we've been thinking about a lot internally. And it's a very good question, and I don't think there is a great answer to it, except yes, consider uncertainty in sort of all calculations.
Thank you so much. And I'm peeking at a time, and I think that this session could have been a whole full day for a rich discussion. It's an extremely important topic. So I will, since I'm unmuted, like to thank all the panelists for this very great session, and then I will pose the final question to Naomi and sort of hand over the mic simultaneously so that you can proceed with the session. And the final question is if there are any plans to develop a starter kit for the global north and any developed countries there. So thank you very much, and over to you.
Yeah. Yes. So responding to that question about our plans to develop starter kits for the global north, and yes, wary about time, so I'm afraid we'll have to cut this session short. But thank you again, everyone, for joining us today. Thank you, Nicolina, Ben, Sebastian, and Roberta for joining us today. Thank you so much.